So basically, every chemical reaction involves some transfer of energy and heat from taking the products into reactions or vice versa. And so we can examine a lot of the aspects of that in just one problem. So let's examine if you were to drop sodium solid into water. These would be your reactants, and these reactants would turn into two products. You would get a hydrogen gas evolving, and you would get a highly caustic sodium hydroxide solution. Here would be your products. Now, we can describe that while this reaction occurs, a certain amount of energy is transferred. In fact, we can draw our reactants and products on a chemical energy diagram, showing how much energy is stored in the bonds of your compounds. Now, chemical energy is a form of potential energy. Potential energy, you may learn from or remember from physics, is the energy of position. So, for example, if you had an airplane 30,000 feet above the ground, it would have a lot of potential energy. That energy could be transferred from one type of energy into kinetic energy, energy of motion, by falling. These are two different types of energy, like kinetic energy or radiant energy. These are all forms of energy which can be transferred from one into another. By the way, no type of energy can be created or destroyed, only transferred from one type of energy into another. So we're on this chemical or potential energy diagram, and we see that as we turn reactants into products, there is a loss of energy. But of course, energy cannot be lost, it's only transferred into one or more other types. When this reaction occurs, the energy released is released either as heat, aka enthalpy, or it's released as work. Okay, so when reactions occur, they can release work as well. In fact, we define energy as being the ability to do work. In fact, the delta E, the change in energy of this reaction, is negative 370.0 kilojoules per mole. And so we could say that energy is released when we have this negative value for our delta E. There's less energy in our compounds after the reaction than before, final minus initial. So why do we have to discuss work here, and how does that relate to heat? Well, for this specific reaction, energy is released as both heat and work, because work is defined as negative P and times the change in delta V. Work is the opposing pressure on your system times the change in volume as the reaction occurs. So, for example, you drop sodium solid into water in this container, which contains just air and water vapor. When you drop the sodium in, that releases hydrogen gas. And so adding hydrogen gas, that increases the volume of the system. So basically, I believe work is distance times force, something like that, which is strongly related to P times delta V. Okay, so some reactions, actually we can sum up here. Delta E is actually heat, or Q, plus work, W. But that's not a big part of the AP exam. We're almost entirely going to be talking about heat in this chapter and on the AP, but this is connected to a variety of issues like how does your car work and what you'll learn in physics. Okay, so we examined delta E for this reaction, how chemical energy changes, but most of the time in our class we're going to be referring to just the change in enthalpy or heat. You'll see that this is somewhat different than delta E, change in chemical energy. In fact, it's often going to be smaller. For this reaction, the delta H is negative 367.5, whereas the delta E you saw up there was negative 370.0 kilojoules per mole. This delta H, you see that it's negative. As our reactants fall in enthalpy or heat while they turn into products, they will release energy. When you have a negative delta H, that means you're releasing energy. That means you have an exothermic reaction. However, what if you had a positive delta H? That would mean you have an endothermic reaction. This negative and positive delta H, they are derived from the fact that delta H is just F minus HI. So when we say that we have a negative delta H, that means that the HF was actually less than the HI, the initial. So we can use these values in doing a variety of calculations. So let's see, how many kilojoules of heat are released when these 12 grams of sodium are dropped into excess water? So you can see that we have that reaction written out yet again, and we're being careful to show the states of matter here. They're very important in our calculations. And we, at the right, show delta H is equal to negative 367.5 kilojoules per mole. Here we're saying that every time one mole of H2 reacts, 367.5 kilojoules are released. Or what we're saying is every time 2 moles of water react, 367.5 kilojoules per mole are released. We can use these facts to solve this problem. To convert between moles and kilojoules, we can use a unit conversion factor. We take the coefficient in front of our Na in our unit conversion factors. 2 moles of sodium per 365.5 kilojoules, or 367.5 kilojoules per 2 moles of sodium. So we use this equation to get that 2 and plug it in for our number of moles. This is almost like a basic stoichiometry problem. And now that unit conversion factor, it allows us to convert from moles into to kilojoules. So we want to go from grams of sodium into kilojoules. Grams of sodium into kilojoules, we're going to go via moles. Go to your happy place. So grams of sodium into moles of sodium, and then for every 2 moles of sodium, there's 367.5 kilojoules. So you can go ahead and calculate then that 95.95 kilojoules are released when 12.00 grams of sodium are dropped into excess water. Thanks for watching, guys.